Hello, everyone. My name is Oleksii, and Bernard was talking about Tether a little bit, and I just want to set a context about what I'm doing and been doing with crypto. So in 2015, I started working at Tether, and basically we built Tether. I'm not talking about the Omni protocol, which is used for the actual coins transfers, but we built the service. And I finished working at Tether in the end of 2015, and from that point I'm working in NBSafe. And in NBSafe we are doing different services and products which are mostly based on Ethereum. So for more than a year in our company, we've been telling our clients that you don't need new blockchains. There's already many, and you just need to utilize what we have already. So I never really looked into other blockchains because I was focused on the Ethereum and making sure that I understand everything, that I can work with it efficiently and can develop products on it. And that was till the events of the year ago. So somewhere in the beginning of the June last year, there happened a series of ICOs which put Ethereum on a very high load, so that all the transactions of all the normal users were suffering of very long slowdowns. And so from that point of time, I started to think that maybe Ethereum is depleted at least for now, and we might look for something else. And one of my friends said that there is this thing called Hashgraph, and he finds it promising. So I wanted to look into it and understand it. And so I just want to share the knowledge of my own research about how it works, and to maybe destroy some myths about it, what it is and what it is not. And so let's talk about the Hashgraph. Okay, so the Hashgraph is not a currency, it's not a platform, it's not a ledger of something, it's not a database, it's not all these things. It's like not some another Bitcoin or another Ethereum. So the Hashgraph is just a consensus algorithm and nothing more. So it's just the set of rules that allow a fixed set of members, which is contrary to some other consensus algorithms. It allows a fixed set of members to decide on the order of events, of some events that they are interested in. So from my own experience, in order to understand something, the best way to do it is by inventing this something. So if you want to understand Bitcoin, you just need to invent Bitcoin from scratch. If you want to understand Ethereum, you need to invent it. If you want to understand some consensus algorithms, you need to invent it. And in the process of inventing them, by solving the problems, by using the technologies that you're trying to invent, you will understand it on the deepest level. So let's try to invent the Hashgraph. We have a fixed set of members, say 3 people, who wants to interact with each other and being sure that they are on the same page. So the same problem that is being solved by Bitcoin, by Ethereum, but they were specifically with currencies. On Hashgraph, we don't have currencies, we just have a way to agree on the order of events. So we have 3 people, and we are passing each other messages, authorized messages, signed messages, and everything works till the moment when we want to decide whenever in what order these messages happen. And we want to do this so that everyone agrees that all the events that we produced have this particular order. And we cannot do this by just sending messages to each other, because I created messages at second 0, you received it at first second, the other member received it at second, and you don't know, like we don't have a way to decide when it really happened. So we define a set of rules that will allow us to do that. And how we are doing that, the idea is that we are starting to pass the knowledge to each other. So not just messages, how we do in other consensus algorithms. We're not just passing the messages, we're passing the knowledge about what we already know about all the other participants, all the other members. So at every point, like every now and then, I'm telling the other member that everything I know till this very moment. So I'm telling them that I know what other participants know till this moment and what I know till this moment. So, for example, one participant telling the other that he knows only something. And this other participant, when receiving this information, he writes it down to himself that he received this information at this point of time, and it says that that participant knows this amount of information. Then another participant says what he knows to somebody else, and so it continues. They're just telling each other what they know about all the others. And so in the end, so it continues indefinitely. And in the end, you come to a state when every member knows what other member knows about some set of events down the history. So, say somewhere there upstairs in the future, all the members, all three of them, will know that every one of them know about this basic, about this first events in history. So everybody will know that everybody will have proofs from each other that they know about this event and when they knew about them, when they get the knowledge. So these numbers that they put there is the numbers, like it's the seconds. If we start, history started from second 0, is the numbers is at what second particular participant received the knowledge. So the middle participant received the knowledge about the first event on second 1. The right participant received some knowledge on second 2, then second 3, second 5, and so on. And now they define a set of rules that based on the same knowledge. So they have the same knowledge. They have all the same information. And if you have the same information, you can run a set of rules on it that will sort this information in particular order. And this order will be the same for everyone as long as you have the same information as the input. So the very basic idea how they do it, they see that this first event on the left participant were seen by every other participant on the seconds 2, 3, and 5. So they just take all of them, take the middle one, and they decide that this event happened on the 3rd second in history. That's it. Now they go for the every other event. So they go. They cannot sort the middle one yet because they don't know when every other, like it's not in the example when every other participant get the knowledge about it. So they only can decide on this two on the sides. So this one was learned from the middle one, learned about it on the 1st second. He itself learned about it on the 2nd second, and the first one on the 5th. So the process is the same. They just take all the information about when everyone knew about the event, take the middle one. They know that this event happened at the second in history. Now, so the constraint was that all the members should know about the knowledge of everyone else. But that cannot happen in the ideal world. Well, like in the real world, it can happen in ideal, but not in the real. So they decided this set of rules does not require everyone to know everything. They only require that 2/3 of all the participants to have the same knowledge, and it should be enough to decide on the order of events. And whenever this 3rd participant will come online, he will, at some point of time, his events that were offline for a long time, they will come online, and at that point of time, they will be able to decide on the order of that events. But the order of the events that was decided by 2/3 will be unchanged. there is a popular thing among other consensus algorithms, which is called the Sybil attack. The Sybil attack is when some party can gather the unfair amount of influence over the network. So the Hashgraph is not susceptible to this attack because the number of members is fixed. Nobody can get in, nobody can get out. So as long as the majority of the initial members are honest, everything will work. And yeah, and the Hashgraph doesn't specify any ways of how to. Yeah.
That's a very strong assumption. You are assuming everybody's state doesn't change. You could be compromised then.
What do you mean? But I can be compromised.
If
Yeah.
nobody's compromised, your
Yeah.
behavior is compromised. So
Yeah.
you don't have.
Yeah, that's right. But the thing is that the idea is that 2/3 will be honest. So even if 1/3 is compromised, that's all right. Till the 2/3 are okay.
You have no ability to fix. That's the problem.
Yes. So yeah, and that's the thing about the Hashgraph. It only specifies that. So as long as these constraints are complete, it will work. So if you want to make it more robust, you just need to build on top of it. You need to find a way how to deal with this problem. But that's Hashgraph doesn't say about it anything. So it's a next layer. So yeah, this is the event structure and how it looks. So what we have here is the hash of the so self-parent hash is the it means the event that was produced by the same member, and the other parent hash is the event that was produced by other member, and they both ended up in the same event. Then you have transactions in it, but the consensus, Hashgraph consensus doesn't say anything about the transaction, so you can put anything you want there. As long as members know what to do with it, they will do whatever they need because they will be ordered. Then you have a timestamp when you created this event, so when you receive the information, and you put your signature for everybody else to know that this is you. And there is a funny thing about it. So the signature, if we talk about the elliptic curve signatures, it is at least 66 bytes. And the timestamp, if we talk about the second timestamp, it is at least 4 bytes. Everything else can be great, like you can have no payload, you can have, instead of like putting the hashes there, you can like optimize that greatly to some small amounts of data, but this you cannot change. So you have 66 and 70 bytes. So in total, 70 bytes is transferred from every member to every other member every second to achieve consensus. So you can imagine that the more members you have in your set, the more transfers each second happens from every member to every other member. So it is a quadratic relation. And yeah, so efficiency considerations. Yeah, it goes up. So total consensus bandwidth is at least 70 multiplied by squared n, and where n is the number of participants. So it's a quadratic relation. And so if you have a set of 1,000 members, it will generate of half a gigabit per second of traffic just to achieve the consensus. So it doesn't include the transactions, it doesn't include everything, it's just the overhead for the consensus itself. So to sort the events, to agree on the order, you'll need this amount of traffic generated by the network. Though it's not that scary, because every member will require only a half a megabit, and that's purely achievable even on the cell phone internet. Though if you look, so yeah, this is one of the things that that shows us that Hashgraph is not a panacea, at least. And so if you look, for example, at proof of work, the overhead there actually is minimal, because what you need to do in Bitcoin, you just need to send one block every 10 minutes to all the participants, and that's like nothing. It will be like, okay, even if a block is 2 megabytes, you need to send it to 1,000 participants. They need to do it only once per 10 minutes. So it's just very, very small amount of traffic. And another thing, even if this all works, and for example, you imagine the Ethereum, which is just the same Ethereum, but instead of proof of work or proof of stake, we put the hash graph as the consensus layer there, and all of a sudden you have thousands of transactions per second. The next problem that you face right away, and that we are facing already right now, is that currently Ethereum nodes having a hard time being in sync with all the network. Because just in order to process the transactions and in order to update your local database of all this that happen inside of the network, you already spend a lot of computing power. And if you will have more transactions, you will just have to increase the computing power of every node. So this will be the next bottleneck which will be hit, I guess, just right after we have the throughput of transactions, we'll start to deal with new problems. Yeah, so what I said about the Bitcoin, the bandwidth is linear because no matter how many nodes you have, you just only need to send something once in a time. And yeah, and so on the last note, so the hash graph is a consensus algorithm for a fixed set of members, where more than 2 of the members are considered to be honest. Yeah, more than 2/3. It says more. It doesn't waste resources in a way how it is done in Bitcoin or proof of work consensus algorithms, because every event generated during the consensus achievement is used in order to find the order of events. And no any artificial slowdowns is needed. Just pass your messages as fast as you can to all the others and you'll come to consensus. That's it.
Questions? I want to ask a question about if we will use it, this consensus hash graph or other PBFT family consensus in public blockchain. Is it will work or it's will work only for private blockchain? How we can create rules for changing validator to?
Yeah, so the major problem of the hash graph is that it doesn't specify the rules for changing the member set. And without the changing of member set, you cannot have a really decentralized network because you cannot decide one time, put the servers all over the planet, and then decide, okay, we'll work from that point. So yeah, this is a very important question that is currently trying to be solved by different companies and by one at least. And the approach that I know right now that is being taken and being researched and probably being implemented is that every now and then all the members are they're including in their messages, they're including votes about adding or removing the participants from the set. And so again, by 2/3 of participants wanting to add some other members, the member set will be updated and increased. And also if they find out that some members are dishonest or offline for long periods of time, they can also vote to remove them. So this is very basic idea. I don't know how to implement it properly. I didn't think about it too much, but that's probably the way you need to investigate in order to understand if it can be public or not.
It's a follow-up question. So one of the key things that I'm kind of noticing with all the new blockchain protocols is governance. EOS is being the classic. And what you're kind of pointing out right now is a challenge that Hashgraph is having right now. Do you have any thoughts on what people should think about when they build protocols?
When they build protocols, I'm not really interested. I'm mostly interested in people been using the protocols that been built by somebody else. So yeah, the thing is that the company who say that they invented the hash graph and who wants to make a public network of it, they want to put a lot of governance inside, and they are explicitly stating that they think that it is impossible to have a robust network and robust platform without enough governance. And I don't like this idea, though, and I'm not doing anything about it. So I just hope, I hope to see how it will work from from their implementation, and then maybe somebody will come up with a way how to make it robust without governance.
Hi. Hi, thanks very much for the talk. Idan Yago. So I really liked that you tried to give a sense of where Hashgraph, what the trade-offs are for Hashgraph. I'm curious, given what you've said about these trade-offs, what do you think Hashgraph is for? In other words, what are the use cases that you think this particular set of trade-offs is particularly well suited for?
So, basic on this, I'd say so when you have a huge volume of changes, you can only sustain them if they are very small changes. So I'd say the hash graph is very usable if you have for example, just a currency transfer, like a basic Bitcoin functionality. You just can transfer every action that you can make is just decrease one balance and increase another one, because with this small amount of resources you will need to spend to update your database, you'll be able to process a lot of it, and there won't be a bottleneck of your computational power with almost any amount of transactions per second. So I'd say as Hashgraph can allow you to have lots of throughput, you need to have every single piece of this information to be of a small influence. So yeah, it should suit well. I guess it should suit well for as a currency, as a layer for consensus for currency, and I don't think it will suit well something as big as complex smart contracts, for example.
Hi, thank you very much. I wanted to ask, so you're saying that Hashgraph is mainly suitable for permission private blockchain?
No.
Limited number.
It is just that the protocol itself is only defined for the, you cannot say that it is public if it's with a set number of members, right? So it is just on the level of the protocol, it doesn't allow you to be public.
Okay.
But you can invent it on top of it. You can make it public by inventing.
Okay, fine. So from an enterprise point of view, if you have a permission blockchain, does it work on any platform, or it works on a very specific set of platforms? Example, can Ethereum switch off the default one and we use this? Or Hyperledger can switch off their default one and we can use this?
I believe that, so again, this consensus layer is very, very low level, and so any blockchains or other distributed ledger technologies can switch to the Hashgraph consensus, and possibly it will just continue working.
Thank you.
Hi, thanks for your presentation. My question is, how do you deal with finality in Hashgraph?
Yeah, so the idea is that when every participant, or more than 2/3 of participants, have the same knowledge about everything that happened at some point of time in the beginning of the history, they can run the same set of rules on this input data. So as long as you have the same input data and the same set of rules, in the end you will have the same result. And the idea is that you run this set of rules when you have, when you know that everybody knows everything. And so when everybody knows everything and you have proofs of that, nothing can change from that point of time. You just need to set an order, but that input data will never change. So the finality is achieved at the moment when the events are first time ordered. When the set of rules allows you to order the events, from that point of time, the order can never change. And this is this is one sweet thing about the Hashgraph against the proof of work, is that in proof of work, there is no finality. There is just ever decreasing chance of changes to be made in the history. But in Hashgraph, you have finality as soon as you know the order.
If I try to choose PBFT family protocol, why I will use Hashgraph If we choose PBFT protocol with a leader election, like Tendermint, like PBFT, you don't need exponential traffic because in Hashgraph you send all messages to all participants. Why I will choose Hashgraph and why I because I mean that why we need to invent protocol without leader election, but if we try to invent protocol without leader election, we get many traffic.
I cannot answer to your question because, as I said before, I'm no good in any other technologies beyond Ethereum and the Hashgraph, and I'm not even considering myself good at Hashgraph. So I didn't look much into Tendermint. I didn't look much into I didn't look at all in them. So I cannot have a whole answer or whole opinion. So I just don't have opinion on them.
Okay, I have two questions. First question is, what is, based on experiments, optimal number of validating nodes in Hashgraph?
So there is I didn't perform such experiments, but the company that is trying to run the public Hashgraph based ledger is presented some tests of how they try to what is the throughput and what is the latency to achieve the finality. And one thing that I don't like about what they shown is that they made experiments of putting different number of nodes from 2 to 128 in different parts of the world. So for example, all the nodes in America, or all the nodes in America and Europe, all the nodes spread evenly throughout the globe. And they presented how the latency changes with the number of nodes and with the throughput. And so it's shown that if you have 128 nodes spread throughout the world, the latency will be already 20 seconds to achieve finality. So after sending a transaction, in 20 seconds you will know that it found its place in the history, and the order will not be changed. But at the same time, they are telling that they expect for the thousands of nodes to quickly grow around the globe. And with the thousands of globes, you will have finality times of minutes and maybe tenths of minutes. So it is not a big number. So I'd say not more than 1,000 for sure, and probably around 100.
Okay, thank you. And yes, and second was about latency. You started to reply already about this question. But I think Hashgraph is better for sidechains, not for mine blockchain. It's I think other protocols, for example, 15 seconds in Ethereum, it's absolutely enough to synchronize all network, and in Hashgraph it will be up to minute in same situation.
That's right, but if you remember, so it's up to a minute, but much more in this minute will happen than in Ethereum. So, for example, 10,000 of transactions in Hashgraph over that 1,000 in Ethereum. So, but yeah, we need experiments. We need to see how it will work. I'm not looking that far.